Introduction to area between curves. The learning target is I can find the area between two curves. So you want to make sure that you have your notes and you take your notes for this. You're going to be asked to do one problem and submit it into Google Classroom. All right, so we have so far been finding areas below curves over certain intervals. I've been saying like from 0 to 2 or 0 to 1. That's over a certain x interval on the x-axis. But now we're going to practice finding areas between two curves. Sometimes you might even have three curves, but today's lesson we're just doing two. Label the graphs below. So this right here is a parabola, y equals x squared. We have a line right here, y equals x. So before we had some experience finding the area, let's say under the function x squared. If we do an integral symbol, and I could say what's the area between 0 and 1, you would shade the region under the graph, and the shading stops on the x-axis, and you're basically going to be asked to calculate like this area right here. Or I could have said between 0 and 2, and then you have a larger area under the curve to calculate. Remember, the area under the curve stops at the x-axis here. So that's a problem that we've been used to. Or if you had something like y equals x, you could again set up an integral and then calculate, like say from 0 to 1 or 0 to 1.5. Or, right, you could make a triangle, right, under the curve. It's like a triangle, and you could use geometry to find the area under the curve. You could do that. Either way would work. But what if I said this? What if I want to find the area between this parabola and this line? The area that encompasses between the two. I'll let you think about this. And then think about, well, between what x interval would I set up my integral for? Between what two numbers on the x-axis would I need to calculate the region that encompasses between the two graphs? So this area right here, if I was to shade this little sliver of area. So I'll let you process that, and then I'll go over it. I mean, you could pause and see if you could try to figure it out. Generally, if we were in class, we'd have a little bit of a discussion about how to do this, and maybe you can come up with some ideas, and I pull from that, and we create how to do it. Well, let's see. All right, some definitions. So here we go, everybody. If you have two functions, let's say one's f and one's g, like one's x squared, one's x, to find the area, you basically subtract the larger function from the smaller function. By larger, I mean the one that's more above the other. This is the formula to find the area between two curves. You're going to set up the integral between a and b, whatever a and b is. I'll talk about that in a second. And you'll do top function minus the bottom function with respect to x. That's what dx means. To solve for these kinds of problems, we need to find where the two curves intersect. That is the answer. That is the interval. Where both graphs intersect is where you start calculating the area and where you end calculating the area. That is where the A and the B will be. So we need to find where they intersect. Let's go over the steps though. Step 1, find where the two functions intersect. Step 2, find which function is larger, or determine which function is larger or taller. And C is going to be subtract that larger function from the smaller, and then you take the integral. Those are going to be the steps for finding the area between two functions. Let's do some examples. Or I'm sorry, we're going to continue with this example, right? We were still investigating what is the area between y equals x squared and y equals x. Well, how do you find that intersection, which was step 1? To find the intersection, this is how you do it. You set the two y's equal to each other and solve for x. This process usually involves factoring or sometimes even the quadratic formula. Let's show some work below. So what do I mean? And why do I have to set the two y's equal to each other? Basically, if the two y's are equal to each other, and I know I'm going to kind of go back here, but I have to. Got to show visually how this looks like. Take this out. That's another lesson. Yeah, save. Okay, something happened. Anyway, go right here. So for example, what I was saying, in order to find where the two functions intersect, you have to see where the two y's are equal. Notice that where the two graphs intersect, the y values are the same. Like visually, you could see that the y value for both functions is going to be 1. The y value right here for both functions is going to be 0. So that's what I mean by setting the y's equal to each other. Because when the y's are equal to each other, that is when your x's are also equal, and that's where you get your two coordinates where the functions are the same. So that's why it ends up working. But let's go ahead and do the process together so you could see how to algebraically make sense of this. Alright, so I colored my two y's. Those were my two functions. Cool. Set these two functions equal to each other, like so. That's what I mean when I say set y's equal to each other. Now we got to solve for x. Maybe you could figure it out by substitution, like what number squared gives me itself, right? You could kind of already guess here, like, oh, if x is 0, 0 squared is also 0. That works. But then what would be the other intersection point? And you could start testing it out like that if you want. Or you could use some algebra, and let me show you how to do this. And I think I'm going to use the factoring method. So step 1 is to bring all the x's to one side. So I think I'm going to move this over by subtracting it, like so. Now that I have this set up, what I'm going to do is I'm going to factor out the a common multiple between x squared and x. Common multiple between the two is x, so I'm going to go ahead and factor out an x. When I factor out an x, I get this. And again, you could double check your work, because if I was to distribute this x back in, I get my original. So kind of think of this like backward distribution. The next thing you want to do is you want to solve for this equation. So x times x minus 1 is equal to 0. Now, if you remember from pre-calculus, we had this thing where it's like, if this is equal to 0, then it's true. Or if this is equal to 0, then that's true, because if you multiply by 0, that gives you the same solution. So basically, how you solve for this is you set each of these components equal to 0. Well, this one right here, x equals to 0, is already solved for. Then I have to go ahead and set this one equal to 0. So x minus 1 equals 0. Let's go ahead and solve for x. Great, I get the other intersection point at x equals 1. And notice, if I was to plug this back into my original, it's going to be true. 0 squared minus 0 is 0. That one checks out. Then this one right here, 1 squared is 1 minus 1. That does equal 0. That point also checks out. So it does make sense when you use this process. Now, the formal name for this, I just remembered, but in pre-calculus, it was the zero product property. That was that rule that if you have two numbers or two variables that are multiplied with each other and they equal to 0, that means that either one of them could be 0, and either one of those zeros gets you the solution. So that's why you said both of them equal to 0, and then you solve from there. So that's where that comes from. All right. So now that we have the two intersection points, we're ready to continue with our steps. So then the next step was we're going to subtract, I believe. And here's the visual. So it looks like the taller or the larger function. What I mean by taller or larger, I mean which function is above the other. Look at that red line right here. This red line is above this parabola. So basically this red line right here is going to be taller or larger than the parabola that's in green right here, between x equals 0 and x equals 1. See that? It matches up algebraically with what we got. Now that we have now we can find the area between these two functions by subtracting that bigger function from the smaller. So here we go. So this is my setup here. So 0 and 1 came from what we did before. We found the two x values that the two curves intersected at. My x, y equals x, was the taller or larger function, minus the smaller function, which was x squared. And I told you guys that I found that out visually, which one's taller, which one's larger. And I'll explain. Let's say, like, what if I don't know which one's taller or larger, right? What if I don't have a calculator or Desmos on the AP exam? How am I going to tell? Well, I'll give you guys some tips on that at the end of this problem. All right, the next step I did is I went ahead and took the antiderivative, right? And or the integral. So the antiderivative of x is x squared over 2. The antiderivative of x squared is just x cubed over 3. Now this we're going to do from 0 to 1. So I'm going to plug in 1 and then subtract after plugging in 0. This is nice because this right here is just going to all become 0. We're going to be left over with, it looks like 1/2 minus 1/3, which is 2/6 or 1/3. So our solution, the area between these two curves, is going to be 1/3 units squared, whatever that area is. We don't have units right here. So you could just say units squared is fine. Yep, so that's the area. That's the sliver of this area right here. Okay, let's jump into some examples, just from further practice, so we can get this this process in. So find the area between these two functions. So step 1, let's find where these two functions intersect. So I color coded my y's, set them equal to each other. Next step is move all the variables and numbers to the left hand side. So I subtracted x and subtracted 2, all to the left side. Next thing you want to do is you factor. The other one was kind of straightforward because all I had to do was factor out an x. Now for this one right here, you're going to have to use the box method, right, to factor this. So that means you're going to have to use a box. But if you use the box, you're going to get this factored form. Now, I need to say this. Now, if you're a little bit confused as to how I factored this and need a review on the box method, please make an appointment with me in office hours so I can show you how that works out. But if you factor this using the box method, you get x plus 1 times x minus 2 equals 0. Once you have this, we're going to utilize the zero product property. Whenever you have a multiplication of two terms and they're equal to 0, what's true is that this is equal to 0 and this is equal to 0. So you solve each of them. And that's how you get your two solutions. So from here, I'm going to minus 1. From here, I'm going to add 2. So it looks like my intersection points is going to be at x equals -1 and at x equals 2. That's where these two functions intersect on the x. Now that I have that, I could, and by the way, please have these in your notes. Don't just move on like I'm doing right now. It's because I need more space here. Now that you have that, you're going to go ahead and you're going to plug in. So we had -1 to 2. That's where our integral is going to be. We're going to do the taller function, x plus 2, minus the smaller function, x squared. Now you could say, well, how do I know that x plus 2 is the taller or the larger function? Well, I know it because it's a line, and a line usually just goes up, and a parabola I know starts off low and then goes up. So it shoots up kind of like a U, so I kind of know that the line is above that U. Now here's the thing. So it's not a huge issue if, let's say, I did x squared minus x plus 2. It wouldn't be a huge issue because what would end up happening is that your area is negative. All you have to do is change your area to positive and you'll get the same answer. So basically, if you get a negative area, then you might have made a mistake. You just change it to positive and that's fine. You could also double check on Desmos. That's also okay too if you want to see which function is above which, so that you don't make that mistake. That's fine as well. All right. So after I did x plus 2 minus x squared, I took the antiderivative. So the antiderivative of x is x squared divided by 2 plus the antiderivative of 2 is 2x minus, and then the antiderivative of x squared is x to the third, all divided by 3. Once I have the antiderivative, you're going to go ahead and plug in. So you're going to plug in the top number, subtract, plug in the bottom. This one is going to get a little bit long. This is the type of problem that you want to be careful with. But let's go ahead and simplify this. So I get this is going to be 2 plus 4, and that's minus 8 over 3. Again, use brackets to keep your work organized, but just follow along. So this is -1 to the third power is -1. But because there's a negative, that becomes positive, double negative right there. Then you can further simplify. And I'll say this, I'm totally okay if you're comfortable with changing all of this to decimals, but I went ahead and just converted all my numbers to fractions if you're the fraction type of person. So you should get 27 over 6 for this problem. Let's go ahead and do one more, and then the last one is going to be a U-try. So one more example, example 2, let's find the area between y equals x squared plus 3 and y equals 4. Alright, color code. Set the two y's equal to each other. Move all the numbers and variables to the left-hand side. We just have a 4 right there. Okay, x squared minus 1 equals 0. Now, you could do box method, or you can remember that this is actually equal to this in factored form. And again, if you need some help with box method and how to factor this out, office hours is where I want to see you at, or you could just shoot me a text on Remind, and I'm happy to show you the box method for that. Now again, I'm going to utilize zero product property. We're going to set each of those equal to 0. And when each of those is equal to 0, you're going to get -1 here and +1 over here. So that's where these two functions right here intersect. Now that we have that, let's set up our integral. We're going to subtract taller function minus the smaller function. Again, I know that y equals 4 is going to be taller than this one because this is a horizontal line at y equals 4, and this is a parabola, so I still think it goes under. Again, you could double check that with Desmos. So there we go. I did taller function minus the smaller function. Notice how I did parentheses around this. That means this negative will be distributing, so be careful. And notice how I put the two intersection points right here on my integral. That's going to give me the area. Distribute. All right, let's take the antiderivative. Oh, actually, before you're going to be doing too much work if you jump into the antiderivative. So first do 4 minus 3. That's going to lessen our work. Now let's take the antiderivative. Antiderivative of 1 is going to be x. Antiderivative of x squared is x to the third over 3. Now we're going to go ahead and plug in. We're going to do 1, and then we're going to subtract, and then plug in -1. Like so. Be very careful. I recommend using brackets. Let's simplify our work. And again, if you want to use decimals, you're free to. Right here, what I'm doing is equivalent fractions. For example, 1 is the same thing as 3 over 3. Over here, -1 is going to be -3 over 3. So basically, I changed all the fractions so that they're over 3. Then I went ahead and combined. Double negative gives me a positive. I got 4 over 3. And again, if you did this in the calculator, you'd get a decimal, and that's fine. Again, feel free to pause this video wherever you need to pause at, but that is the end of it. So you could also go back, text me a remind. This one right here is the one that you're going to be doing for your assignment on Google Classroom. And again, feel free to text me a remind to even check your work for you. I'm very happy to do that. Other than that, good luck, y'all.